Okay, so we started with central limit theorem on the inferential statistics. We are trying to infer about population. Inference means, right, trying to get some information, right? So trying to understand. Inference means kind of understanding. We are trying to get some understanding about population by looking at samples. When you take multiple samples and take means of them and take mean of all those means, that's going to be population's mean equal to population mean. That's one thing. And second thing is these means, right, n number of samples means are going to be normally distributed, and we can calculate the standard deviation of these means using sigma by square root of n. This is the central limit theorem. We saw an example there, right? Here we don't have much information. With whatever we have, we actually try to get the standard deviation of the sampling distribution of means, and then we found the confidence interval of the population being population mean coming between 100 and 124. Okay, then we started looking into statistical significance. When something new is found, and there is something existing and something new is found, we need to see whether the new thing is how significant. Right? If in the old setup, if we can reproduce the new thing more than 5 number of times, we will say the new thing is not significant. That 5 is a thumb rule. It's a kind of it is based on experiment. That's called as p-value, probability, right? 5 how out of 100, 5 out of 100 or 0.05 is the threshold. Alpha we call it as the I forgot the name here. We call it as alpha, probability, p-value, right? P-value and alpha. The p-value is the probability calculated for the experiment. Alpha is the threshold where we actually look at. For different experiments, this number is going to be different. But in general, statisticians take to 0.05. Yesterday, Lakshmi Narayana was actually trying to say, something is not really true. Right? I said that generally accepted fact is the null hypothesis, but the statement I created may not be right. That's where it is looking like a contradictory thing. Generally accepted fact means whatever we know so far is the generally accepted fact. The new outcome is what we are trying to nullify. What we are trying to see whether it is significant or not. You have something, you found something, you wanted to see the new thing is significant or not. So what we do is we try to take the environmental situations which were there before finding the new thing, or which actually helped find you the new thing, right? New thing is there. Some environmental conditions have helped the new thing happen. So we say that your new thing is not significant. When I say your new thing is not significant, in your old circumstances, the new thing should happen. If in the old circumstances, the new thing is happening more than 5 times out of 100, we say the new thing is not significant. If it is happening less than in your old circumstances, new thing is happening less number of times, we say that is significant. The new thing is significant. The circumstances or the environment or the whatever the drug or device or whatever helped you get the new thing is significant, we say. Did you get it now? New thing and old thing. I was kind of trying to explain it in a different way. Is it meaningful or making sense?
Can you please come again? The statement.
Okay. So there is some old thing we already know, right? I'll talk about a solid example in a minute. Okay. Yesterday, what example I took is not, the statement was not properly framed. So it looks like contradictory, right? So you know something, right? With some environmental conditions, you know something, right? So you found something new, right? With new environmental conditions, okay? New circumstances, you found new thing. Now you need to see how significant your new thing is. Okay, that is the significant statistical significance test. Okay. To say your new thing is significant, we need to find out p-value. Okay. What is our goal now? Statistical significance of new thing we need to find. How significant your new thing is statistically, we need to find. To find that new thing, whether it is statistically significant or not, we will use p-value. P-value. Okay. How to calculate p-value? Okay. To calculate p-value, what you will do is you will take your existing, old known environmental conditions and try to produce the new thing, right? Because in null hypothesis, what we will say, what we know is right, right? What we know is right. The new thing is not right, we'll say in null hypothesis, right? Generally accepted fact is the true, right? In null hypothesis. When I say in generally accepted fact is true, the new thing should happen in known environment, right? The generally accepted environment or circumstance. If the new thing is happening more than 5 number of times out of 100 times, we say the new thing is not significant. Okay, this 5 are the how many number of times the new thing is happening in old environment or old circumstances is called the p-value. Right, 5 is the threshold. 5 is the threshold, but we need to find how many times the new thing is happening in old circumstances. Okay, if the new thing is happening in old circumstances more than 5 number of times, we say the new thing is not significant. Even without your whatever conditions you say, the thing is happening more than 5 number of times. 5 is not a thumb rule. Generally, statisticians take 5 as the threshold, but no, different experiments will have different threshold. Got it? Is it still confusing?
Yeah, I understood.
Right. Let me try to draw this and explain a little bit, right? And then we'll take a simple example. This example will make it more clear. This example is going to be more clear. Okay. Give me 1 second and let me take a whiteboard. Whiteboard, how to take whiteboard. Let me clear this up. Oh, sorry. Oh. Sorry. How to close page? Okay. So page setup, I think. Page setup. Oh. Okay. So there is some experiment, right? And this experiment is in some environmental conditions. Right? The same experiment, right, we conducted with some new environmental conditions. And previously, maybe with old environmental conditions, we were getting maybe 5 outcomes. Okay. We know that we were getting some outcomes. We don't know how, right? How many? Right? We don't know. In the new experiment, I said that I am getting 5 outcomes. Okay. So the statistically this is going to be significant only when these 5 outcomes are, when you conduct experiment 100 number of times, you are getting when you conduct this 100 number of times the experiment, no, not 100 number of times, 100 number of times you are getting maybe, maybe what is that experiment, right? That's a weird thing. Let me take the example and explain. Okay, I think I made the point. You're old, you know something, you found something. To find something, you need some circumstances or environmental conditions. If you can reproduce the new thing without the new environmental conditions 5 times or more in the old conditions, you can say the experiment is not significant. So let me take this example and explain. So here there is a neurologist testing a new drug, right? Response time of a new drug on 100 rats. Okay, subjecting each to neurological stimulus. The mean response time of the injected rat is 1.05 seconds with standard deviation 0.5. The neurologist knows that the mean response time for rat not injected with the drug is 1.2 seconds. So there is a drug. Right, let me wipe this out a little bit. Give me 1 second. So there are 2 things there. One, a drug. Second one is a neurological stimulus. Okay, there is a drug and a stimulus. There were 100 rats. Okay, there were 100 rats, and in the old situations, right? This is the known thing. In the old situations, when drug was injected, right? When only drug was injected to the 100 rats, right? There are 100 rats here, right, in the box, right? The response time, neurological stimulus, I think. Give me 1 second. Yeah, the neurological stimulus. This is, sorry, known thing is neurological stimulus. This is 1 and this is 2. Okay, this is the known thing. So neurological stimulus, right? When the neurological stimulus only got injected, the response time was 1.2 seconds. The response time was 1.2 seconds. Okay, with a standard deviation of we don't know the standard deviation. But now, right, with the new experiment, right, in the new experiment, what this guy did is there are 100 rats. Stimulus was given, right? Along with that, drug is also given. Now he finds that the new experiment, right? The new experiment is giving 1.05, right? The rats are responding very quickly, 1.05 with a standard deviation of 0.5. We'll talk about standard deviation in a moment. Okay. So the response time increased, right? With the new drug, the response time is increased, right? Do you see that? Previously it was 1.2 seconds. Now it is 1.05 seconds. Do you see that? Do you see that?
Yeah, there is an increase.
Right? There is an increase, right? So we need to see whether the new outcome is significant or not, or the drug is significant or not here. In this total experiment, stimulus is common. I said the circumstances or environment, right? Environmental conditions. The old environment, only stimulus. In the new environment, stimulus plus drug. Now the statistical test is going to be, the significance test is going to be for the drug, whether the drug is significant or not. Okay. So null hypothesis is going to be what we know. Generally accepted fact is what? 1.2 seconds, right? In general, we were getting 1.2 seconds, right? I said I found a new drug, and when I injected new drug, I am getting 1.05 seconds response time. We'll look into standard deviation in a moment, right? And you will say like the mean response time is 1.2 seconds only, right? Generally accepted fact I am actually saying. When I say the neurologist knows that the mean response time of not injected drug is 1.2 seconds. What that means? The neurologist knows that the mean response time is not with not injected with the drug is 1.2 seconds means what?
If you only injected the stimulus, then it will take 1.2 seconds time to response.
Yeah, no drug, it takes 1 point. That means what? It was being done many times before, right? Generally accepted fact means only neurological stimulus was given to rats and they found that it is 1.2 seconds. That is generally accepted fact. Okay. Mean response time we are saying. Mean response time means 100 rats you took, only neurological stimulus given, taken response times and taken an average, that is 1.2 seconds. Again, the same experiment was done. Same experiment was done. Right? Like that many times it was done, and everybody knows that when the neurological stimulus was given, it is 1.2 seconds mean response time. So that is generally accepted fact. That means drug has no effect. That's what we are saying. Whatever new thing you said is not right, we are saying. Here the significance test is for drug, right? Significance test is for some new environmental condition. Okay. So significance test is for drug. Drug has no effect. That's what we are saying. That's the null hypothesis. What is the alternate hypothesis? Mean response time is not 1.2 seconds. Drug has affected. It may be either less or more. Okay, it's opposite to null hypothesis. Alternate hypothesis is opposite to null hypothesis. So to say the drug is significant or not, okay, so we need to find out the p-value. We need to find out the p-value. What I said was, this is the old environmental condition. What is the old environmental condition? The stimulus. New environment condition is stimulus plus drug, right? Stimulus plus drug, right? So if I say drug has no effect, what I should get in this old environment, when you give only stimulus to 100 rats, the mean response time should come 1.05. Okay, the mean response time should come 1.05. Okay, so when I say mean response time, right, when you give stimulus, mean response time will oscillate, right? One time it may be 1.5, one time it may be 1.2, other time it may be 1.05, like that it may oscillate. Do you agree? Do you agree with my statement?
Yes. Yes, Ram.
So yeah, so what we are trying to see is whether drug is significant or not. So to say drug is significant, when drug was not injected, are we getting this quicker response or not? That we need to test. That is the statistical significance test here. Got it? What I am going to do, the math I am going to do is going to be, when drug is injected, I am saying it is 1.05. It is quicker, right? In the old environmental condition, how many times I am getting this 1.05 response time? If I am getting too many times, right? When I take n number of samples and try to inject only stimulus, if I am getting 1.05 seconds response time too many times, this test is not significant. This drug is not significant. Did you get the statement?
Okay.
Old environmental conditions, if you are getting 1.05 seconds response time many times, this drug is not significant, right? How many times, that we will see in a moment. Okay, so I am going to do the, use center limit theorem and try to see how many times this response time is coming. This 1.05 response time is coming when the drug was not injected, only stimulus was injected. Okay, if it is happening too many times, this response time is happening too many times, this drug is not significant. How many times? Out of 100 times, if it is more than 5, then this drug is not significant. That is the p-value. Right? We need to calculate how many times it is happening, right? Out of 100, how many times? If it is happening 10 times, right, this drug is not significant. If it is happening 2 times only, this drug is significant, right? In the old environmental condition, I am saying, not here. I should write here. In the out of 100 times, right? If the 0.05 response time is coming 10 times, right? This drug is not significant because the alpha, the p-value, the alpha we have taken is 0.5. What is the p-value here? 10 by 100 is 0.05. This is alpha is 0.05. 0.1, right? 0.1 is greater than 0.05. So we, accept null hypothesis and say this drug is not significant. Okay, if it is happening only 2 times out of 100, it is going to 0.02, right? That means very rarely it is happening. When you give only stimulus, this response time we are getting very rare, right? When you give this drug, right, it is happening quite often. That means this drug is actually affecting whatever new thing is affecting. That's where it is happening very frequently. When the drug was not given, right, the only stimulus was given, this is happening very rare. That means this is working, right? Got it? Got it?
Rama, I was actually thinking the null hypothesis we need to take reverse. Maybe I'm wrong. When
What
we took the
hypothesis?
null hypothesis.
No, this is the way. We have to take this way only. Whatever generally accepted fact is the null hypothesis. Alternate hypothesis is opposite to it. What are we trying to prove here? Why do you think the null hypothesis should be taken the other way around? What are
So
we trying to prove here?
I was thinking we take the mean response time is 1.05 seconds as a null hypothesis, and we check the probability of getting that is more than 5%.
No. Wait for a minute. Let me complete the whole thing and then maybe we can discuss, right? But try to carefully read this problem statement. A neurologist is testing the effect of a drug, right? That is the significance test we need to do it for, drug on response time by injecting 100 rats subjected each to a neurological stimulus. Okay, the neurological stimulus is already there. This guy is testing the drug. Okay, that's the meaning of this statement. The mean of the mean response time of the injected rats with the drug and the device is 1.05 seconds. Okay, with the standard deviation 0.5, right? The neurologist knows that the mean response time not injected, right? This is the old condition, right? The existing condition is 1.2 seconds. What is new here? What is new here? The drug, right? Drug, right?
Yeah.
So does the drug influence the response time? That's the question. Also is about drug only. The statistical significance test is about the drug. Okay. So we need to take the generally accepted fact. The new thing is drug, right? So the drug has no effect. That is the null hypothesis. Okay, what we know is mean response time is 1.2 seconds only. When I say mean response time is 1.2 seconds only, indirectly I am saying that drug has no effect. That's the null hypothesis. Whatever generally known, we are trying to nullify. Researchers are trying to nullify this. That's where we call it as null hypothesis. When you nullify this, right, then your new drug is, is significant. Okay. So let me complete and then we'll come back and discuss. Maybe I'm sure that this is right. This is what the way I have taken is right. Okay. The mean response time is not equal to 1.2 seconds is the alternate hypothesis. It is like opposite to the null hypothesis, an alternate hypothesis. Now we need to calculate p-value. What is p-value? Out of 100 times, how many times you are getting the 1.5, 1.05 seconds in the known situation or the null hypothesis situation. Okay, null hypothesis situation, how many times you are getting? How to calculate that? So the p-value is null hypothesis. Drug has no effect. It is quite common to get 1.05 seconds mean response time for many samples, more than 50 out of more than 50 out of 1000 or more than 5 out of 100. Okay, 100 rats each. 1000 samples, 100 rats each. Okay, so what I'm saying, null hypothesis mean response time is 1.2 seconds means what I'm saying is drug has no effect. That is one first point I'm saying indirectly, right? And if you elaborate that a little more, it is quite common to get 1.05 seconds mean response time. Okay, for many samples, right? For many samples, every time you take a sample, 100 rat sample, the mean response time will change, because all the time all rats will not respond the same way, because of their immunity power and whatever the capabilities each rat having, the rats will respond in different ways. So out of 1000 samples, each of 100, 50 out, more than 50 are getting 1.05 seconds. That's what the statement says statistically. Did you get this statement? Did you understand this statement? Yes, no?
Yes.
Yes.
Yeah. So p-value. Now what is the p-value we need to calculate? To say that the drug is significant, what value we need to find? I am actually trying to see. That is called as p-value. Okay. Probability of getting mean response time 1.05 when drug is not injected. When drug is not injected, we wanted to see the mean response time, right? How many times, probability, how many times out of 100 the mean response time is getting 1.05. So to do that, what we need to do is, let's find out p-value, probability of getting mean response time when drug was not injected. Assumption, we know only one sample, right? Sample standard deviation 0.5, right? Hence best estimation we are taking as 0.5 only, right? Here in this total statement, we know when the drug was not injected, what is the mean response time? We know. This means what? It is a mean of means, right? They have taken many samples in the history. And they actually took the means of those samples, right? Injected neurological stimulus and took the means of those samples, and this is mean of means. That's why they are saying generally it is 1.2 seconds. Got it? Mean response time is 1.2 seconds means these sampling distributions mean it is. Did you get that statement?
Yes.
Right? This is sampling distributions means it is. Okay. They have taken, something already, that means it was the experiment was done many times and means were taken, and mean of mean is what we actually try to speak. This is the sampling distributions mean it is, okay? And the standard deviation, population standard deviation, we don't know, right? They would have done experiment on maybe 10,000 rats, or maybe 1,000 rats, or maybe 100,000 rats, but we don't know the standard deviation of it. So whatever standard deviation we know, we'll take that as population standard deviation. That is one approximation. That's what I did here, right? We know the mean response time 1.2 seconds. We know this is from many samples and their means. This is mean of sampling distribution mean. That means this is actually population's mean. From central limit theorem, when you take n number of samples and take mean of them, and then mean of all those means, that is going to be equal to the population's mean. That is one part, right? When we say many samples and their means, it is a sampling distribution of means. The sampling distribution from means approaches normal distribution, okay? So this is one more statement we need to remember. And the standard error of the sampling distribution of means is sigma by square root of n. Sample size is 100. Sigma, we have assumed that it is 0.05. So it's going to be 0.05. 0.05 is the standard error. Okay, let me show you pictorially. See this, you can see this clearly, right? Should I expand it a little bit? You can see. Can you see?
Yeah, I can.
Yes, sir.
Yeah. So this is actually sampling distribution of means of all those experiments conducted historically when the new drug was not injected. Do you agree with my statement? When new drug was not injected, only neurological stimulus was injected. This is a sampling distribution of means, and the mean of those means is 1.2 seconds. Do you agree with the statement I made? Cecilia,
Yeah.
I think you know a little bit of statistics here, so I think you may be knowing more than what I know. But do you agree with the statement I made, or anything wrong there?
I was actually thinking, we need to calculate this for the new circumstances, because the standard deviation.
So how can you calculate for the new circumstances? Because new circumstances, you don't have. It is not that you are conducting the experiment now. It is like this. I came up with this statement saying that my drug is working better. The rats are responding faster. I said, right? Now you cannot catch hold of 10,000 rats now and do the experiment again, right? Do you agree with my statement? With my new drug, right? Is there a possibility that you can catch hold of 10,000 rats and then do the experiment again? Without doing that experiment again, we are trying to see whether it is significant or not. To do that, the experiment was conducted already with many rats in the history with only stimulus. And we know that it is 1.2 seconds mean response time, right? And when you conducted the experiment many times, it is normally distributed. The means are normally distributed. Each time you can, an x-axis, right? It is the mean response time of each experiment. Got it? Conducted previously, only with stimulus, right? This we know, right? Without doing the experiment with the new drug, we are trying to find out whether the drug is statistically significant or not. Once we statistically know that it is significant, right, we will do that experiment. We will spend money, right? The companies actually spend money in catching hold of rats and then injecting them and taking staff and all that. Got it? The importance of statistics and statistical significance test. Got it? Do you agree now?
Yeah.
Right? So that's what you are actually thinking like the other way. What you thought was real in mathematics perspective. If it is real mathematics, right? I am saying real mathematics because statistics is not really mathematics. It is like approximation. It is all Like, Telugulo జాతకం చెప్పడం అంటారు కదా, ఆ టైప్ ఇది, right? So it is like, palmistry, right? They look at palm and try to tell you what is going to happen. It may happen, it may not happen. In statistics also it is true. If your numbers are really good like this, right, then your outcome, your statistical test outcome is going to be reliable. If numbers are not good like this apples experiment, right, your outcome is not going to be reliable. Okay, so this is the sampling distribution of means of already known data. I know 1.2 as the mean of means, and I don't know the standard deviation of the population. What is population here? All the rats that were injected with neurological stimulus only, and their response times, each individual rat's response time. Each individual rat's response time, if I know, I can calculate the standard deviation of the population. Do you agree? Did you get my statement? Here,
Yes.
right here, I know the mean response time. If I know each experiment, okay, maybe my statement, two statements I have to make. One, each rat's response time I know, I can calculate population standard deviation, right? Or if I know they would have conducted 10,000 experiments before, or 1,000 experiments of each 100 rats. If I know all the means, individual means of those 1,000 experiments, 1,000 mean numbers, then also I can calculate standard deviation of the sampling distribution of means. Do you agree? Do you
Yes.
agree? All right.
Yes.
So now we don't have those two, right? That's where we are taking the best approximation of the standard deviation. Whatever one sample standard deviation we know, we took it and we calculated the standard error. We call it a standard error because this may be true, this may not be true. The sampling distribution means standard deviation we calculated using this formula. This may be kind of close to it, right? So we took this and then we are trying to see 1.05 how far is from 1.2, right? What I said here, in the existing situation without injecting the drug, how frequently this 1.05 is happening. That's what we need to see, right? So there are experiments done. 68% of the experiments mean response time is falling between 1.15 and 1.25. How do I know? I am saying 68% of the experiments mean response time is between 1.15 and 1.25. How do I know? How did I calculate that?
One standard deviation.
So one
standard deviation. 1.12 minus 0.05. What is 0.05 here? This one, right? 0.05 is the standard error. Standard deviation. Right? I know standard deviation and mean, I can calculate one standard deviation, right? What is this one standard deviation? 68% of my experiments outcomes. What are the experiments? Mean response times of the rats when only stimulus was injected. What is this? This graph is about only stimulus was injected, no drug. 1.15 to 1.25 are within 68%. 95% of the times it is happening 1.10 and 1.15. It is 1 minus 2 into 0.05, 1.2 plus 2 into 0.05. Right? 3 standard deviations away, right? 1.05, 1.35. In when the drug was not injected, 95% of the times this response time is not coming. Do you agree? When the drug was not injected, only the stimulus was injected, 1.05 response time is coming, 95% of the times it is not coming. You took a sample, did the injected stimulus, took the mean, again, right, took the 100 rats, injected stimulus, took the mean, injected stimulus, took the mean. 95% of the times this response time is not coming. Okay. Very rarely it is happening. Very rarely it is happening. This 0.05 and less response time is happening very rarely. What is this area here? So it is 99.7 is the 3 standard deviations away, right? 99.7% of the times it is not happening. That means 100 minus 99.7 we have to take. That is 0.3%. 0.3% of the times the 1.05 response time is coming or more. It is actually tails, right? This is one left tail, this is right tail. On the left tail only we are actually looking at, right? Especially this 1.05 thing, right? On the left tail only we are looking at. So that means we need to take the, divided by 2. 0.15% of the times this is happening when the drug was not injected. Only the stimulus was given 0.15 percent of the time. When I say 0.15%, right, it's going to be 0.15 by 100. It is 0.0015. 0.0015 is the p-value of this experiment, of this statistical significance test. For the drug, right, the p-value is 0.0015. That is less than the alpha. Alpha is what? 0.005. When the p-value of a statistical significance test is less than the alpha significance level, alpha is called a significance level, you reject the null hypothesis. What is null hypothesis? The mean response time is 1.2 seconds is rejected. So the mean response time, right, not equal to 1.2 seconds. It may be less, it may be more. That's what the statistical significance test is saying. That means drug is significant. Drug has effect, right? Now, without conducting the experiment by injecting drug and stimulus, we found that the drug is significant. Now we can, company can invest on the drug and whatever the experiment, because especially in the clinical trials, right, the drug companies actually spend millions and billions of dollars. Before they spend, right, these tests are going to be useful. Okay, so statistical significance tests are going to be useful, and with ML, right, we can reduce the, we can actually automate this whole thing, whole process of finding whether it is significant or not. Got it? Any questions here?
I think
Now,
the percentage is 0.15 is already a percentage, right? Divided.
That's where I divided. That's where it became 0.0015. Right, 0.003 it is, right? 3% means 0.3% means 0.003, right? I said it is less than, but the statement is not right. We need to take the half. 0.0015 is the p-value, right? What is p-value? You need to understand. What is p-value? You need to understand. What is p-value? How frequently the new thing is happening in the old circumstances is the p-value. Right? Simple statement. The new thing is happening in the old circumstances is the p-value. How frequently? Got it?
Yeah, Rama, that is correct. But we are taking this 0.15 for the left side and 0.15 right side. So that is already a percentage, right?
Yeah, percentage.
So do we need to divide it again by 100?
Yes, I did here. See this here?
Yeah,
So it's a
my question is,
test.
do we need that? Do we need to divide it by again 100? Because it's already percentage, right?
This 0.3 is actually sum of these two. When you do two-tail test, right? This is called as two-tail test. I am saying mean response time not equal to 1.2. That means less than and more than, right? This is called as two-tail test. Then p-value becomes 0.05. If you do only left-tail test, right, it's going to be 0.0015. You need to divide this by 2. Got it? This and this are same. I am summing these two and actually taking that as 0.3. I may not have got your question clearly. I think you and me are saying the same thing. I'm thinking like that. Is that right? No? No? Yes? I didn't get you. Did you get my point, or is there any confusion still? Sorry?
I think he's saying that because it's already percentage, you should not divide again with 100. I think that's what I could understand.
We should.
Yeah, we should, because 100%,
We should divide.
100% means probability of 1.
1, yes, right. P value is 1, probability is 1. We are calculating probability here, right? Probability, P value is probability. Okay, you are saying you should not divide. We should divide. Yeah, that statement, maybe Giri statement is right. 100% means 1 probability. Probability is always going to be between 0 and 1, right? Do you agree now, Shashi?
Actually, I got disconnected.
Oh, okay.
So what I will do is I will just go through this video again today, and if I'm still confused, then we will discuss.
Okay. So anybody else has got any questions here?
Yeah, Rama, small confusion here. Can you go to the previous slide? Yeah, here if you see that the whole environment, mean is 1.2 seconds, but there is no standard deviation. We don't know what is the standard deviation.
Yeah.
But the new environment of means is 1.05 and the standard deviation is 0.5, right? But in the below slide, you're showing that the normal distribution, the bell curve for the old environment, and you are using the standard deviation of the new environment.
No, it is not the standard deviation of the new environment. I took this as the best approximation of the population standard deviation and calculated the standard error here. That is 0.05, not 0.5, 0.5.
0.5 here we can okay.
So when sigma by square root of n is what?
Yeah, that is standard error.
Standard error is when do you use standard error? To calculate the standard deviation of the sampling distribution of means, right?
Yes.
So I am using 0.5 divided by square root of sample size, which is 0.05. It is not 0.5, 0.05. That's one thing. Maybe your statement is this standard deviation should not be taken as the standard deviation here, right?
Yes, this 0.05 standard error is applied to the new environment, not for the old, right? How you are like taking the old?
So you are saying, basically what you are saying is 0.5 should not be taken here to calculate standard error, right? That's what your statement is, right?
No, standard error, we can take the standard error for the new environment, like because the samples are related to new environment only, not for the old environment.
when you are saying null hypothesis, right? You are saying the new drug has got no effect. Then why? How does it matter, right? Whether I take the old environment standard deviation or new environment standard deviation, it doesn't matter because null hypothesis is already saying that your drug is not useful, right? When my drug is not useful, I'll take the old mean and the new standard deviation.
Okay, we can take it in that case. Okay.
It is statistics, right? We have this information, we don't have anything else, so we are taking it. If we had the standard deviation of this old environment, right, we would have taken that and calculated the standard error.
Okay. Now got it.
So the perfection is not going to work when you are actually doing statistics. Perfection.
Yeah.
So
still we need to tune my minds, because still we are thinking about perfection. Always coming to the statistics, it's not 100% perfection, right?
Yeah, 100%. No, it is like what we have and what we can produce.
Based on that, yeah. Yes, got it.
So it is really true, even in real-time environment. Many times when you are making predictions, you will not have all the information. So the central limit theorem is going to help you a lot. We have seen 2 examples here. It's an Apple example, right? That is really a bad example, right? There is nothing there. There is no data at all. And we assumed something and we try to come out with some result. Right?
Yes. Okay.
So this is a bit reasonable. If you look at the statement and the data we have, right, it is a bit reasonable.
Yeah. So here also we assume that old environment standard deviation is 0.05.
Yeah, old environment's population standard deviation is 0.5. We assume, and using that we calculated the standard error or the standard deviation of the sampling distribution of means.
Yes.
Using that we actually tried to see how far this 1.05 is from 1.2. It is too far, right? In general, when the new drug was not injected, 99.7% of the times it is not happening. That means the drug is significant. As soon as you injected the drug, it has given me the 1.05 seconds response time. So the drug is significant, right? Whether the medicine is working or not, how will you see? You took Ayurvedic medicine, you are still facing the problem. You took English medicine, the problem is gone. So you say the drug is working, right? Like that it is.
Yeah.
So without doing the experiment, we are trying to find out whether the drug is significant or not using some statistical calculations. Okay.
Yes, Rama, thank you.
Everybody convinced? I think Sheshiram is still not convinced. So have a look at it and come back to it. And,
yeah, sure.
And right, this is like how to do statistical significance test and what is p-value. The most important thing we need to take is what is p-value. P-value is the probability of happening, the new probability of getting the new thing in the old environment. In null hypothesis situation, how many times the new thing is happening? That is the p-value. Out of 100 times, how many times the new thing is happening in the null hypothesis situation? That is the p-value. You need to remember this one point. Out of the 2-hour, almost 3-hour class, right? You need to remember this one point. And again, I tried to take the sampling distribution, standard deviations, and it will get used, make you use it to think in this direction. When you say data scientist or an artificial intelligence engineer, right? The thought process should change. When you are doing development, right? It was always like you got a requirement and you have a tool and you are actually, building something. It is not like that here. You need to think a lot, and then thinking is more than working here. Okay, so you need to change the thought process a bit. Okay, the next thing is z-test and t-test. There are two kinds of tests. When you take whole population and calculate mean, right? You call it as mu. When you take whole population and calculate standard deviation, you call it as sigma. Okay. When you take sample and calculate the variance or standard deviation, you call it as S. When you take the sample and calculate the mean, you call it as X bar. Okay, or capital M. Okay. Similarly, when you do a test, right, you call it as Z statistics or T statistics, depending on whether it is population or standard deviation. But sometimes, give me 1 second. When we take sample, right? When we take a sample, that time also we say sometimes it is we need to decide whether it is t-test or z-test. So first question we need to ask is, do we have population standard deviation or not? Right? If we don't have population standard deviation, we call that as t-test. Formula is like same, only n-1 or n, right? So if you have population standard deviation, if you don't have population standard deviation, how big the sample may be, you call it as t-test only. Okay, or you do t-test only. Use these formulas. Okay. If population standard deviation is there, right, is sample size greater than 30. If sample size greater than 30, right, you use z-score calculation formulas. Okay. If the sample size is less than 30, right, you use t-test. Why am I showing this is, on Monday we'll see the connectivity between statistics and machine learning. Okay, in that we'll actually do t-test, or we see the outputs from the machine learning algorithms as t-tests, because we don't know the population standard deviation. Okay, in real time you will not know population standard deviation because population is ever growing. That is one thing. And model training we always do with samples only. How big may be, right? It may be 1 billion records, but still it is a sample. Okay, so when you know standard deviation of the population and the sample size is more than 30, then only we'll use z-test formulas. In other cases, right, we'll do t-test only. Got it? When to use z-test and when to use t-test. Okay, Monday we'll connect these dots. So for today, right, I'll say that's it. And if you have any questions, right, you can ask. Or if you want to discuss, right, we can discuss the topics.
Rama, I missed one point here. For t-test, what is the x-bar?
Mean.
Oh, x-bar is mean. Okay.
Yeah. Mean of the data points is x-bar. This is variance formula. You say sigma, right? It's going to be square root. That is standard deviation. Right?
Okay.
Got it?
Yeah,
Yeah, that's it for today. Now, if you want, we can discuss if you want to know more.